Welcome back. In this lecture, I will sum up the learnings from linear step polymerization and then move to nonlinear step polymerization. So, these are the topics I plan to cover in this lecture. Now, we have discussed different aspects of step growth polymerization, linear step growth polymerization, and understood how to control the molecular weight, what are the kinetics associated with this linear step polymerization and what are the limitations and all these things. So, basically let me summarize that our target is to increase or the molecular weight or actually to achieve the target molecular weight during our synthesis. So, for that let me again revise and basically sum up the learnings we learned during this step growth linear polymerization to basically say what are the requirements for achieving high molecular weight in linear step growth polymerization. Now, we know that the reaction rates are generally very slow except few cases. In fact, the reaction rate for polycarbonate step polymerization rate constant is of the order of 10 to the power minus 3 liter mole inverse second inverse in the range of 150 to 250 degree centigrade. Now, so this is quite a slow reaction process. There are few examples like reaction between acid chloride with alcohol or amines are quite faster, but in general the reaction rate is quite slow. So, in that case we basically we need to do the reaction at high temperature and we need to do the reaction at high temperature and the concentration of monomers or the functional groups should be high. Now, from our Carothers equation we know that the conversion should be close to 1 and it is better to have externally catalyzed reaction rather than self catalyzed reaction, and because the reaction takes longer time we must choose monomers or the chemical structure of the polymer such that it can sustain or it can survive that high temperature condition. So, it should have enough thermal and oxidative stability. So, we must design monomers and polymers such a way that they have enough thermal and oxidative stability, and we also should ensure that the reactions are carried out in inert atmosphere to remove to basically avoid any thermal and oxidative degradation of the polymers. We also know that to build high molecular weight our reaction stoichiometric ratio should be at close to 1 as possible. Hence, we need to have very high pure monomer. Otherwise, if the monomers are impure, then we do not know what are the actual molar ratio of functional groups. Additionally, if the monomers are not pure, then we do not know whether the impurities actually can act as chain stopper or not. If they act as chain stopper, then synthesizing high molecular weight will be difficult. And we know if we want to control the molecular weight for our purpose, then we can actually control the molecular weight by changing the stoichiometry of functional groups or deliberately adding small molecular weight monofunctional molecules which are also called chain stoppers. Now, equilibrium considerations are also prime important, as we discussed that to have a decent or acceptable molecular weight, we must remove the small molecular condensate out of the reaction as much as possible, so that we can push the equilibrium towards polymerization, and we should always have the equilibrium constant for the reactions higher. So, we should design the monomers and polymers, monomers such that the reaction between the functional groups are of high feasibility, so that the equilibrium constant is high. Now, we must also ensure that no or minimum side reaction, because if the side reaction happen, then the stoichiometry can be off from the targeted stoichiometry, or we might actually land up generating some monofunctional chain stopper, or some chemicals which might degrade or actually accelerate the oxidative or thermal stability of the polymers. And we also prefer to do the reaction with high concentration monomer to reduce the cyclization, and proper choice of monomers need to be also taken care of. One of the also important thing is the accessibility of functional groups. The polymers which we are synthesizing, during the polymerization, it should not precipitate from the reaction. So, it should be actually soluble in the medium or the reaction mixture, especially at low molecular weight region. If the polymers which are getting synthesized, they come out or get precipitated from the reaction mixture at lower molecular weight, then it is not possible to build high molecular weight. And of course, as we know, this all the polymerization processes are exothermic, because in the polymerization process we are creating new bonds, and any bond creation is exothermic process. So, during the polymerization process, the heat is generated, and as a result the local temperature of the mixture actually becomes high. So, it might, if the local temperature is become much higher, then it can actually degrade or do some side reaction in the polymerization process. So, managing the heat during polymerization is a very important thing, and generally we do by proper stirring, so that no local hotspots are created, or the viscosity, or you can, if you can do in a solution phase, then obviously viscosity problems are much lower. So, well stirring is actually a must thing to manage viscosity as well as manage the heat generation in the system. Even though doing all these things, if we find that we are not able to synthesize the target molecular weight, then there are few troubleshooting instruction that you must analyze the trap where you are collecting that small molecular condensate, to check whether some monomers also coming, because we are applying high vacuum and high temperature. So, there is a possibility that some monomers may also evaporate or vaporize and come at that low pressure. So, you please check, one should check the trap to find out whether monomers has come, and then if that is the case, then you need to change or compensate the monomer loss by changing the molar ratio of the functional groups, and also we can change the temperature pressure profile to reduce the monomer loss from the system. And we can also analyze the product to find out whether the chains are stopped by a different molecule than what expected. In that case, there is a possibility that chain stoppers actually produced during the reaction as a result of degradation or side reaction. So, we must understand the chemistry of those reactions and try to minimize this, and of course, there are other ways to try by changing the catalyst, and if you are doing the solution, then changing the solvent. So, these are some troubleshooting instruction you should follow if we are yourself doing some linear step polymerization and not able to build the molecular weight you are targeting. Okay, now we will move to the next topic, which is nonlinear step polymerization, and till now we have been discussing in case of linear step polymerization where the monomer functionality were 2. We are either using AB type monomer or AA plus BB type monomer. Now, in case we have value of monomer greater than 2, for example, if we take this monomer plus a monomer having F is 3. So, F is 3 in this case. Now, in this case what type of polymer we will get? We will get AB, 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 and if one of these gets in the chain, then we get a and so on. So, in this case if we have a functionality 3, then we are getting branch structure. So, these are branched polymer. Now, in this case the reaction rate actually is faster compared to linear step polymerization, and also the increase in degrees of polymerization with conversion, the relation between with P in this case of nonlinear polymerization, Xn actually goes up the higher rate compared to a linear polymerization with respect to P. If we talk about molecular weight distribution in this case, then we without deriving the formula we can write, which gives us this formula. So, at R is equal to 1 and P is equal to 1, we get x w by x n, which is the dispersity value, which is given by 1 plus 1 by F. So, in this case the polymers produced are narrower, polymers are narrower or have narrow distribution compared to a linear step growth polymerization. Now, we move to the second case where now in case of instead of A B type monomer we have AA plus BB type monomer. So, in this case we have AA plus BB plus we are adding a multifunctional monomer where F is greater than equals to 3 in this particular case. Now, if we write the structure, then we get this polymer AA. Now, if one of these gets in, so like we have a monomer which is F is equal to 3, then that will get in somewhere in the chain and we again get and so on. Now, this can again react with another monomer and chain can proceed, and see now if we this again react with another trifunctional monomer. See, we have another monomer here, then this can react with like this. So, in this case we have this is one linear chain, this is another linear chain, and we have these two chains are connected with this bridge, which are called cross links. These are cross links. So, we are getting a cross link polymer in this particular case, and if the monomer ratio is such that or the reaction goes for longer time, then one time it might happen that these reactions this actually can react and all the polymer chains can get tied up with each other through cross links, and you get a almost like infinite molecular weight polymer, and we get a network polymer in this case. So, in nonlinear step polymerization, monomers with a F greater than 2 has a dramatic effect upon the structure and molar mass of the polymer formed, as we just seen from the two example I showed in just few minutes. And in the early stage of this reaction, the polymers has a branch structure, as I just discussed, shown the example, and with time, if because of the branch structure, the molecular weight or the molar mass actually increases more rapidly with the extent of reaction than a linear step polymerization, and with time further branching reaction leads to ultimately to formation of a complex network structure that I showed, which are properties are quite different from those from the linear polymerization. And once these entire polymer chains present are linked to each other and there is enough concentration of such polymers in the solvent, we get a gelation or gel formation. What is gel? Gel is a state where the reaction mixture form a viscous liquid to a solid mass, and solid mass show no tendency to flow. So, gelation is an abrupt change in the reaction, change of the reaction mixture from a viscous liquid to a solid gel which has no tendency to flow, and the concentration or the time at when this gelation happen, we call this point as a gel point. Now, we can, so during gel formation, as you can understand that we actually get a kind of different polymer chains, all the polymer chains in the system, they are connected to each other and you have a network formation. We can have, so this is network formation and ultimately this polymer does not flow at all, form a gel, and you can appreciate that the molecular weight or degrees of polymerization in this case would be infinity, because all the polymers are linked to each other. So, the effective molecular weight in this case is infinity. Now, if you want to use Carothers equations to find out at what conversion we will get this value of x n equals to infinity, then we will take a simplest situation scenario where we are taking A is to B 2 functional group as 1:1 and we are defining F average plus we have the other group. A is to B, the ratio of functional group A and B is 1:1, that is the simplest case, molar ratio of course we are talking about, and we define F average is the average number of functional groups present per molecule, which equals to summation of Ni by Ni. So, Ni is the number of molecules with functionality of Fi and this is the total number of molecules. So, at beginning we have N 0 is the number of molecules at t is equal to 0. So, N 0 and F average would be number of functional groups at t is equal to 0. Now, if at some time t, if n is the number of molecules present at time t, then we know that x n is given by n 0 by n. Now, if we have, so what is the number of molecules reacted? So, how many molecules reacted in this case? How many molecules reacted? So, number of molecules reacted is given by N 0 minus initial number of molecules and the number present at now. So, number of functional groups reacted, each molecule, disappearance of molecules means 2 functional groups reacted. So, 2 into N 0 minus N. So, each to have disappear one molecule. So, like if you have a plus BB reaction, and if I react this and make a dimer, then total number of molecule disappeared is from 2 minus 1. So, 1 molecule disappeared, how many functional groups reacted? 2 into 1. So, each molecule disappearance is equivalent to reaction of 2 functional groups. So, the total number of functional groups reacted is 2 N 0 minus N. So, the conversion is the fraction of functional groups reacted N 0 minus N divided by N 0 F average, which was the initial number of functional group, total number of functional group. So, P is given by 2 by F average minus 2 by x n F average, because N 0 by N is x n, as N 0 by N is x n. So, which means if we again rearrange it, we get 2 by 2 minus F average into P. Now, for a linear polymerization, if you just compare, for linear step polymerization, F average is 2, which mean in this case x n is 1 minus 1 by P, leads to the original Carothers equation. Now, to gel formation, what is x n? X n is infinity. So, in that case P c, which is the critical conversion where gel formation takes place, is given by just placing x n is equal to infinity, we get 2 by F average. P c is where the moleculars become infinity. So, as we increase the average value of functionality, we will get gelation at much lower concentration of the reaction. So, let us move to the other systems, like we can get we gave one example of this system. We gave an example A plus class B. In this case we have given example, so formation of network, formation. We have shown the example where in this case we have seen that it leads to branching. Now, you can also do yourself and see that all these cases, this leads to network formation or cross linking when f is greater than greater than 3. So, these are some of the systems you can design if you want to get gel formation or network formation, and if the average is f average is higher, then you can actually achieve, or one can actually achieve the gel formation at lower conversion. With this, I think I will just give you some of the important example of network polymers by synthesized using step polymerization. And one very important example is phenol formaldehyde resin, and typically this network formation product of step polymers are generally termed as or named as resins, and one such example is phenol formaldehyde resin. Formaldehyde for this reaction is F is 2, whereas a phenol has 3 places to react. So, it has actually F is equal to 3. Now, if you compare the other two example, this is F is equal to 4 and the melanin is F is equal to 3, and in case of phenol formaldehyde reaction between these two, we get 4 possible different product which basically react with each other and other formaldehyde to produce network structure. Similarly, another important network polymer is epoxy resin, and in this case at the beginning low molecular weight P polymer containing epoxide groups N groups are formed, and they generally are formed by reacting epichlorohydrin with the sodium salt of bisphenol A, forming pre-polymer small molecular weight polymer with epoxy N groups, and then using functionality more than 3 monomers with functionality monomer 3, we can actually cross link these epoxy pre-polymers to make network polymer. Remember, in this case this is functionality is 2 plus 2, unlike the reaction with say amine with acid where this functionality was 1 plus 1, and because it is reacting with epoxide, it has two capability form 2 covalent bond. So, it has a functionality 2 plus 2 4. So, it can form a network like this. Now, as we can understand that once network formation happen, it is difficult to handle because you cannot take out by or reprocess these things. So, typically what is done, it is actually done in the mold, in the final shape what you want to give. The first the pre-polymers are made in a liquid and then the pre-polymers are added to the mold and further cross linking reaction happen using this type of cross linker. And network polymers were the first produced step polymerization was among the first type of synthetic polymers that to be commercially used or commercialized and often termed as resins, and the polymers are completely intractable. So, at the stage when network chains are generated, the polymerization must be carried out within a mold to produce the reactor product. So, the final cross linking reaction with the P polymer must be carried out within the mold, so that it gives you the final product. Okay, with this we come to this end of this module, and one should able to understand the mechanism of step growth polymerization. The student should be able to relate the number of degrees of polymerization with conversion, and students should be able to know how the step molecular weight or degree of polymerization in linear step polymerization can be controlled using stoichiometric imbalance or using chain stopper, how the molecular distribution expression in case of linear step polymerization, how to calculate molecular weight and PDI or polydispersity index or the dispersity. They should know the kinetics of step polymerization, and they should appreciate that externally catalyzed reaction are faster than internally catalyzed or self catalyzed reaction, and in that respect they should also realize and that the equal reactivity of functional groups and its justification. Students should be predict the number of degree of polymerization for step polymerization in case of closed system and in a open and driven system, and student realize that for a step polymerization to happen, it is always preferable to remove the small molecular condensate maximum extent possible. And I given some example of different synthetic process. Student can just look for it as information, and also they should know what are the general characteristics and process condition reactor to make a or synthesized linear step polymer successfully, what are the problem and what are the troubleshooting, and then we finally talk that how to synthesize branch or cross link polymer. With this we come to end of this module 2.